In this screencast, we will look at another example of a truth table that will help us introduce the notion of a biconditional statement. Consider the following example. P implies Q and Q implies P. And let's complete the truth table for this. Let's first look at each piece of the conjunction. The first piece is P implies Q. Remember that this is only false when P is true and Q is false. The only time that this happens is in this second entry right here. In all other cases, P implies Q will be true. When we look at the next column, Q implies P, this will again only be false when Q is true and P is false. That happens in the third entry of this column. Again, all of the other entries will be true, so let's complete those entries now. Now we want to consider the conjunction of these two. Again, we need P implies Q to be true, and we need Q implies P to be true. The only time that this happens is in the first row and last row. In each of the other two entries, at least one of the two pieces will be false, so the conjunction is false in these two cases. Notice in this example that the compound statement is true only when P and Q were both true, or when P and Q were both false. And the compound statement is false when P and Q have different truth values in the middle two rows. This means that P and Q are equivalent statements. This example that we are looking at here is known as a biconditional statement, combining two conditional statements together. Let's look at a formal definition of a biconditional statement. If P and Q are statements, the biconditional statement, denoted with a double-headed arrow between the P and the Q, is the compound statement that can be written as P if and only if Q, and it is true only when P and Q have the same truth value. This is exactly what we were looking at in the previous example, but let's look and see how P if and only if Q relates to that example. Recall that P implies Q can be written as P only if Q, and also that Q implies P could be written as P if Q. Of course, putting an and between these two statements and combining them together gives you P if and only if Q. When we recall the alternate wording possibilities for the implication P implies Q, we can combine them together for P implies Q and Q implies P and get alternate wording for the biconditional statement. So the biconditional statement is by definition written as P if and only if Q, but the alternate wordings that we get, we could simply say P implies Q and Q implies P. We might also say P is necessary and sufficient for Q, and as we already stated in the example, a biconditional means that P is equivalent to Q. A common shorthand notation for the if and only if statement is the initials IFF between the P and the Q, and this you will commonly see in writing. Of course, there are several other alternate wordings that are possible as well, and we can use any of these interchangeably within the mathematical statements that we make in the future.